Oh, hello, everybody. We are going to start with the seminar, the webinar of the International PhD School on Advanced Oxidation Processes. This webinar is in the exclude of the several webinars I'm going to present in this school. And today we have the pleasure to have Professor José Antonio Sánchez Pérez, who is going to talk us about the Photo-Fenton process and the fundamentals and application to wastewater treatment. This webinar is in the frame of the International PhD School. I'm going to introduce this PhD school. This school was an initiative of academic and scientists in the beginning from European groups, but in the last year, several groups from other countries has been involved in the school, and now we changed the name from European PhD School to International PhD School on Advanced Oxidation Processes. The objective of this school, the first objective is to promote the higher education of young scientifics in the research of advanced oxidation processes. This International PhD School is coordinated by the Professor Luigi Riso from the University of Salerno, and we have Sixto Malato as coordinator of the European partners, and Professor Ricardo Torres Palma coordinating the Latin American partners. The school is formed by 69 scientific committees members from 49 institutions from 21 different countries. Up to now, we have 160 PhD students and 46 alumni. The International PhD School include different initiatives that can be summarized in the organization of a specific training event, promoting networking and collaborating among school members, and one of the awarding of the International PhD on advanced association process with the award for thesis in these fields. To be part of the PhD school as PhD student, you have to comply to basic criteria. That is that the thesis need to be in the frame of the advanced oxidation processes in this field, and that the supervisor have to be member of the school. But if you want to apply for the school, you can put in contact with Luigi Riso. You have the email. Here are some pictures about the International PhD school, and one of the most important activities of the PhD school is the organization of summer school. We have organized three schools in different summers from 2015. In Salerno, the first one in Porto, in Portugal, and the last one in Alcoy. Unfortunately, the pandemic, the COVID pandemic, has forced that this is the last one we have organized, but we have the intention of continuing with these summer schools in a face-to-face mode. But because of the pandemic also, we have organized several webinar program for the 2020-2021 2021 course that in this XLU is include the webinar of the Professor José Antonio Sánchez Pérez, which is going to be today. If you want more information about this seminar, the webinar, you can go to the information in the website of the PhD school. Professor José Antonio Sánchez Pérez is going to present this webinar. He's a full professor at the Department of Chemical Engineering of the University of Almería in Spain. He's director of the Solar Energy Research Center, CIESOL, and he's also director of the University Chair Aqualia about the integral water cycle. He has supervised 19 PhD theses in different fields, such as biotechnology of microalgae, filamentous fungi, fermentation, and water treatment. He's author of more than 170 scientific publications in International Journal of High Impact, and currently is involved in 5 national and international research projects, all of them about solar water treatment, disinfection, and contamination, and contaminants emerging concern removal using the Photo-Fenton process for wastewater reuse. Professor Sánchez Pérez has developed his research line in the Solar Energy Research Centers, CIESOL, since the foundation in 2005. CIESOL is a joint center between the University of Almería and the Plataforma Solar de Almería. The center is located on the northern side of the University of Almería and in a single-story building, built with the support of a European project, ARFRISOL, about bioclimatic architecture and solar cooling. In this sense, CIESOL was built using bioclimatic standard and solar cooling, and it's designed in climate and efficient energy use. In this center, there is a interdisciplinary center in which we have different professionals like physics, chemists, biologists, industrial engineers, and chemical engineers. Some of the objectives of this, or the focus of this center, is the medium and high temperature solar thermal energy, the design optimization of solar thermal cooling heating system, the water treatment, and also the integration of solar thermal and photovoltaic energy in building. Here we have the structure of CIESOL, and I don't go to give you more information about the center, but the center includes 6 fundamental unit function, and many undergraduate and master students develop their curricular practice in the center since the foundation, in a large percentage from the University of Almería, but in some cases from other Spanish and European universities. In this sense, there's also many PhD students have done stays in the center, making collaboration in the frame of the SPERA project. Here you have the information, which is an horizon project with the aims of these projects is to boost scientific collaboration among the leading European research institutions in solar technologies, offering European research and industry access to the best research and test infrastructures and creating a virtual European labs. Sánchez Pérez is one of the functional unit of CIESOL is the water treatment unit. Professor Sánchez Pérez is the head of this unit, which is focused on the photocatalysis for the removal of toxic substances and water disinfection and its combination with advanced biological methods. In this end, he worked on the use of solar and UV LED Photo-Fenton for the contamination and disinfection of wastewater, and the optimization of the operation and development of new technology and water treatment economics also. And in this research line this is the frame of the webinar. It's going to present by the Professor Sánchez Pérez. I don't know if Professor Sánchez Pérez, you are ready to share your screen and start with the webinar.
Okay. Thank you, José Luis, for your nice introduction. I would like to thank to the International PhD for inviting me to this talk. And I'm going to share my presentation. I hope you can see the presentation.
Yes.
Okay. So, as said before, the title is Solar Photo-Fenton Process, Fundamentals and Application to Wastewater Treatment. First of all, we will speak about some fundamentals of the Photo-Fenton process, starting with the main reaction involved in the process. These are the Fenton reaction, that is the hydrogen peroxide with ferrous ion, giving ferric ion and an hydroxyl radical. This reaction is very fast. And the second reaction is the photoreduction of iron 3, giving again iron 2 and another hydroxyl radical. This reaction is slow and depends on Fenton availability. So if we add both reactions, we can see, as in the picture, a redox cycle between iron 2 and iron 3 with the consumption of hydrogen peroxide and the release of hydroxyl radicals. And this reaction is driven by UVA radiation that came from the sun or from artificial light. As for the reactions, once we have formed the hydroxyl radicals, we have a set of efficient reactions, that is mainly the oxidation of the organic matter present in the water, giving oxidized organic matter and releasing CO2. To this, this is a chain reaction with the radicals, and this mechanism gives rise to the release of CO2 and is called mineralization. One of these reactions, if we consider only one of these reactions, we can take into account the attack of the hydroxyl radical to a given contaminant, giving transformation products, that is organic matter, oxidized organic matter, without considering the release of CO2. But along with this efficient reaction, we have another set of inefficient reactions that are the reaction of hydrogen peroxide with radicals in different steps, giving finally water and molecular oxygen, or the reaction radicals with radicals, giving to water and oxygen. So this inefficient reaction gives rise to the release of oxygen. The Photo-Fenton process is strongly dependent on the pH. Iron 3 is photoactive and soluble at acidic pH, and the value pH 2.8 has been reported as optimal. But we can operate the Photo-Fenton process at neutral pH too. In this case, we have two main problems: ion precipitation to the neutral pH and the presence of bicarbonates, which are a scavenger of hydroxyl radicals. To solve the problem of ion precipitation, we can use ion ejecting complexing agents. And among the different complexing agents, the most popular is EDDS, because it's biodegradable and it's stable in water solution. When designing a Photo-Fenton reactor, it's very important to consider some factors. First, we will see what are the inputs in the design process. We need to consider the type of wastewater. This has a paramount influence in the process, along with the flow rate. Very close to the type of wastewater, we have the contaminant concentration and the type of contaminants, if we want to remove chemical contaminants or biological contaminants. And finally, the process target: mineralization, decontamination, or disinfection, or all of them at once. Okay? So the process target is very, very important. The next set of conditions we have to take into account is the operating condition for the reactor. That is, what is the radiation availability, or the kind of radiation we're going to use, the solar or artificial radiation. We need to choose the pH, acidic or neutral, the iron source and its concentration, and finally, the HO2 concentration we want to use in the treatment. As outputs, taking into account all these factors, we will be able to calculate the reaction kinetics. With these kinetics, we can obtain the reactant consumption and reaction time if we work in batch mode, or the hydraulic residence time if we work in continuous flow mode. Reaction kinetics and the operation mode will give us the tools to calculate the reactor size, that is the liquid depth, and the surface area, and finally the cost of the treatment. We should pay attention to the impact of pollutant concentration. As said before, it's very close or closely related to the kind of wastewater to be treated. In the case of highly polluted effluent, that is toxic wastewater, typically industrial wastewater, the contaminant concentration should be in the range from milligrams per liter to grams per liter. In this case, the target of the treatment is the organic matter mineralization along with the biodegradability enhancement. To this end, we need a great amount of hydroxyl radicals, and to obtain this amount, we need to work with high concentration of iron, typically 20 milligrams per liter, and high concentration of hydrogen peroxide, typically 1,000 milligrams per liter. As we are going to work with small volume of water, we can work at acidic pH, and the treatment time is generally measured in hours. So it's long treatment. A very different scenario is observed when treating effluents containing microcontaminants, as is the case for treated urban wastewater, where the contaminant concentration is in the range of nanogram per liter, microgram per liter. That is 1,000, 1 million times lower than when treating industrial wastewater. In this case, the target of the treatment should be the parent compound removal and the toxicity removal, the chronic toxicity removal, because normally this kind of water has no acute toxicity, but it shows certain chronic toxicity. To this aim, we need a low amount of hydroxyl radicals, and therefore we use low concentration of ion, typically 5 milligrams per liter, and hydrogen peroxide, between 30 and 50 milligrams per liter. As we pursue to work with large volumes of water, we try to work at a neutral pH, and in this case, the treatment time is in minutes. So the process is much faster than when we treat toxic wastewater. The next parameter we need to take into account between the fundamentals, or among the fundamentals of the Photo-Fenton process, is the radiation. To take into account the effect of radiation, we use different variables. One of them is the normalized illumination times, the now T30 watts. It's a normalized time which use as a reference the UV solar power of 30 watts per square meter. So it's the time of treatment equivalent to an irradiance of 30 watts per square meter. Another variable is the accumulated solar UV energy received per unit of volume of water, now as QUV in kilojoules per liter. And this is an accumulative amount of energy received in the system. Both QUV and T30 watts take into account the irradiance reaching the surface, but not the reactor geometry. And they are useful in case of the reaction rate is limited by light availability. Nonetheless, the most useful variable is the volumetric rate of photon absorption, the VRPA, which combined the effect of ion concentration, the irradiance reaching the reactor surface, the optical properties of the absorbing species, and the liquid depth. The calculation is a little more complicated than the QUV or the T30 watts, but it allows to take into account the radiation in the kinetics of the process. We can consider both the solar fractions, the direct and diffuse, in order to have a complete picture of the radiation inside the reactor. To finish this little or short revision to the fundamentals of the Photo-Fenton process, I would like to speak about the different steps from the water, the kind of water we want to treat, and the treatment goal, and the different steps we need to take before the full-scale design of a solar Photo-Fenton plant. At lab scale, starting from the wastewater characteristics, we can develop a model, a kinetic model. This kinetic model should be validated at pilot plant scale using environmental conditions. And once the model is validated, Taking into account the plant location and historical data of temperature and UV radiation, we can proceed with the design of the reactor. So next, I will show you some study cases of the application of the Photo-Fenton, the solar Photo-Fenton process. First, I will show you some research about the treatment of toxic wastewater, in this case, industrial effluents. Remind, the effluent has highly toxic substances. We work at acidic pH, and we have a high concentration of pollutants, tens or hundreds of milligrams per liter. And the treatment targets are the organic matter mineralization and the biodegradability enhancement by partial oxidation of the pollutants. We have here some research from the treatment of a mixture of 5 pesticides with an initial concentration of 500 milligrams per liter, and the target of the treatment was to reach a 40% of mineralization. In the figure, we can see how the pesticides are degraded much faster than the removal of dissolved organic matter in the medium, that is the mineralization. We have a high consumption of hydrogen peroxide. In this case, we work adding different amounts of 200 milligrams per liter of hydrogen peroxide to avoid the inefficient reactions. And as main features, we can say that we consume more around 1 gram per liter of hydrogen peroxide to reach this target, 40% mineralization. This mineralization allows the biodegradability of the wastewater treated, and we need long reaction times, around 4 hours of treatment at 30 watts per square meter. We can have a kinetic model of the system taking into account the elementary rate laws of the different reaction taking part in the process, and fitting this model to the experimental data. We can use the model to predict the evolution of the dissolved organic carbon, the consumption of hydrogen peroxide, or the release of oxygen due to the inefficient reactions. The next case is the micropollutant removal in treated wastewater. We know that the wastewater treatment plants are efficient for chemical and biological oxygen demand abatement, as well as the removal of some nutrients, mainly nitrogen and phosphorus. But in the treated water, we can find some microcontaminants, mainly pharmaceuticals and some pesticides that can be removed from the treated water by a tertiary treatment, in this case, the Photo-Fenton process. Here, I show some experimental research at neutral pH to change the former example was at acidic pH. Now I'm going to show you some results at neutral pH. First, at lab scale. Okay, when we work with the complex iron 3 EDDS as iron source with a low amount of hydrogen peroxide, and the synthetic wastewater was picked with 100 microgram per liter of acetamiprid. It's a pesticide, a neonicotinoid. And here we have only some research to illustrate what happens when we work at low iron concentration. As we can see in this figure, when we increase the irradiance from 10 to 30 watts per square meter, from 10 to 30, we observe an increase in the reaction rate. That is, the process was photolimited. But when we increase the irradiance from 30 to 50 watts per square meter, we don't observe an increase in the reaction rate. So in this case, we have an excess of photons, and we can say that the reaction is photosaturated. The same effect of photolimitation and photosaturation, depending on the irradiance availability, is observed with the complex iron 3 DDS, which is partially decomposed by the action of the photons. We see that, or we can see here the picture, that increasing irradiance from 10 to 30, we have an increase in the reaction rate, and later, at higher values, we have the same photosaturation process. The kinetics at neutral pH are commonly more complex than at acidic pH. We have more reaction involved in the process, releasing hydroxyl radicals, and the reaction of hydroxyl radicals with intermediate compounds. But as shown at acidic pH, we can work with the same methodology. Starting from the rate law equation, we can fit the model to the experimental data in order to obtain the model parameters. And here we have two examples of the fit of the model to the experimental results with for very different conditions, 5 centimeters of liquid depth and 10 watts per square meter, or 15 centimeters of liquid depth and 40 watts per square meter. We can observe that the model properly fit the experimental results. The next step in the study was the model validation at pilot plant scale. In this case, we used a raised point reactor, RPR, and we validated the results, the model obtained with kinetic parameter from lab scale experiments at pilot plant scale in 2 different days of the year, in winter and in spring. And as shown in the figure, again, we can see a proper fit of the model, or a proper prediction, in this case, prediction better, of the model to the experimental results. With this research, as the treatment time when dealing with micropollutant removal are very short, in a few minutes, the continuous flow operation becomes a requirement for large-scale Photo-Fenton process. So in this case, I would like to show you different research carried out at pilot plant scale with actual wastewater in 2 different operating conditions, acidic pH and neutral pH, with equivalent amount of iron but different source of iron and the same amount of hydrogen peroxide. Here we have a scheme of the reactor and a scheme of the treatment. From the preconditioning of the actual secondary effluent coming from the wastewater treatment plant effluent of the city of Almería. Here we have the solar Photo-Fenton reactor the water enters continuously to the reactor, as well as the ion solution and the hydrogen peroxide solution, and exit the reactor. And after, we have a neutralization step when we work at acidic pH, or a filtration when we work at neutral pH. Here we have a little video of the pilot plant working with the reactor and the neutralization column. And here we have the results. Don't be afraid, because I'm going to explain all the results step by step. But I would like to show you that here we have results from the experiment at acidic pH and at neutral pH, with 3 different hydraulic residence time, 15 minutes, 20 minutes, and 30 minutes, carried out in different days, in May and April 2019, where we can follow, and we use, that is very interesting too, different batches of real secondary effluents, up to 4 different batches with different initial concentration of microcontaminants. As for iron, the profile of iron during the experiments, we can observe that acidic pH, we have a partial loss of iron due to the reaction with phosphate, the precipitation of ferric phosphate. And at neutral pH, we have a precipitation of iron 2 due to the decomposition of the iron 3 EDDS complex. Okay? We observe too that iron 3 EDDS complex concentration increases as HRT decreases. That is expected following the kinetic model. As for the hydrogen peroxide consumption, we obtain more or less the same consumption at both pHs. And in this case, the HO2 conversion increases as HRT increases too. Okay? This is expected to following the kinetics. And considering the removal of micropollutants, contaminants of emerging concern, in this case, we see in the figure, or we can see that at 30 or 20 minutes of HRT, we obtain almost the same removal, a little bit more at acidic pH or higher at acidic pH than at neutral pH, but in both cases, around 80% of micropollutants are removed in continuous flow operation of the pilot plant scale reactor. With these results and using the previously developed kinetics model at acidic pH and at neutral pH, we apply these models to the actual wastewater, considering the removal of 3 different contaminants of emerging concern: the gabapentin, ortho-dismethyl-venlafaxine, and ortho-dismethyl-tramadol. Okay, this is an example at neutral pH, and we can see how the model properly predicts the evolution of the CEC removal for the 2 HRT aside. Okay, 30 minutes and 20 minutes. So with this picture, we can conclude that we have a model, a kinetic model at acidic pH or at neutral pH, able to predict the performance of the reactor with real effluents. So, taking into account this model, we can calculate the treatment capacity of the system, taking a 10-hour operation per day as a reference. And in this graph, or in this picture, we can obtain the treatment capacity as a function of the liquid depth of the reactor and the HRT we are operating in continuous the reactor. The inclined lines are for different HRT, and the colored lines are the goals of the different goals for micropollutant removal. For instance, to obtain a 70% micropollutant removal, we have to work below the curve, the blue line, okay, in this area of the chart. For instance, in the case we would like to remove the 80% of micropollutants using a liquid depth of 20 centimeters, following the red line, we should use a hydraulic residence time of 30 minutes. With these conditions, we can calculate in the vertical X, we can calculate the treatment capacity, the maximum treatment capacity. In this case, is 4 cubic meters per square meter of reactor and per day. With this data, if we take into account the flow rate of the effluent to treat, for instance, 400 cubic meters per day, the ratio between the flow rate and the treatment capacity gives the surface of the reactor, in this case, 100 square meters. So the main geometry of the reactor is given with this methodology. We have the surface and the liquid depth. Okay? As for the cost of the treatment, that was the last item we need to calculate when designing a process. Generally, the treatment at acidic pH is cheaper than working at neutral pH. In this case, the cost of neutral pH is higher due to the very high cost of the EDDS, the completing agent, the iron completing agent. But overall, we can conclude that the total cost is mainly affected by the reactant cost, much more than the amortization cost due to the reactor and the cost of the construction of the reactor. So the main cost is the reactant cost, and that the final cost will depend on the process target. This is very, very important. We have no cost general or no general cost for advanced oxidation processes. We have specific cost for specific process target. And to finish this short talk about the Photo-Fenton process, I would like to show you the first demonstration plant for tertiary treatment of wastewater, secondary effluents, in the frameworks of the life Ulysses project, we designed and constructed a raised pond reactor with an area of 100 square meter, and the liquid depth can be changed from 5 to 20 centimeters. Here we have a general view of the reactor, and here a partial view of the reactor, okay, with the sensor, the curve, and this is the real effluent. I'm going to show you the first test in batch carried out a few days ago, just before the holidays, the Eastern holiday. To start the reactor, we use the most controlled condition, that is pH 2.8, 5 milligram per liter of iron, 50 milligram per liter of hydrogen peroxide, and we added 100 milligram per liter of acetamiprid as a model contaminant in order to follow the kinetic. The reactor volume was 10 cubic meter, and the liquid depth 10 centimeter. And this is the actual secondary effluent from the wastewater treatment plant of the city of Almería. And here we have the primary results of acetamiprid removal. We obtained a high removal. This compound is very hard to be removed by Photo-Fenton. That's why we use. If we are able to remove acetamiprid, other microcontaminants are removed first. The results follow the expected kinetics, and we obtain very encouraging reactors. Because to finish, I'm going to show you the final water. Well, how was the water after the treatment? This is the same. That's the secondary effluent previous to the treatment and after the treatment. Thank you very much for listening, for your attention, and I want to thank to all the people of the group, the water treatment group at CIESOL, who have been working very, very hard to reach this demonstration plant. Thank you very much.
Thank you very much, Professor Sánchez Pérez. Now you can. I want to invite to the student in this webinar to use the chat of the meeting to transmit all the questions for the speaker. I'm going to put the first question to give time for the people to send questions. You have shown different ways to apply Photo-Fenton process, and at the beginning of the presentation you have talked about the different treatment depending on the concentration of contaminants in the water, for high concentration and for the low concentration. I understand that for the high concentration we are talking about, for example, industrial wastewater, and in the case of low concentration we are talking about the secondary effluent especially. And in this sense we could have two different focus for the application of this technology. And I would like to, what do you think about the most important limitation for the implementation of the Photo-Fenton process at industrial scale in both cases?
From my point of view, right now, the most important limitation is the regulation, because the regulation are not encouraging the treatment of the tertiary treatments in the wastewater treatment plants to remove microcontaminants. And with industrial water, we have different strategy that can be alternative to the Photo-Fenton process. But really, from my point of view, what is now slowing down the advance of this technology is the lack of stricter regulation.
Okay, thank you. We have one question in the chat. I'm going to...
Tengo la mano levantada.
César.
Oh, excuse me, César. Please, César, you can ask.
Thank you. Congratulations, Jose Antonio. Beautiful, beautiful. I know very well you have been working during a long time in this field, and now to see beautiful application is very exciting. Congratulations. I have a little question. Is the following. What do you think about the possibility today of taking the surface you use for your reactor, not for the reactor, but for the photovoltaic panels? Because today these panels has efficiency of 20–30%, and to take advantage of this electricity to work in most concentrated way with lamps, because also the LEEDs lamps today are very cheap, very efficient. Then what do you think about that? That could be a future option?
Yes, of course, of course. The future is coming, and the LEDs are now among us. Okay, so we can work with LEDs at UVA radiation. With UVC are not so easy, but to reach 244 nanometers in the LEDs is very expensive now.
Yes.
But now the cost with close to UVC 279 nanometer, the cost is competitive now. So we can develop an intensive Photo-Fenton treatment with this kind of LEDs. Indeed, we are working in this line as an alternative to solar. Yes.
And your system absorbing the visible also, and you don't need the UVC. You need only visible and one part of the and the UVB and UVA. Beautiful, because that could be very important for the region where there is not so much place, in the region you need. It's okay. Thank you very much.
Thank you.
Okay, well, we have more question in the chat. Since the process is very rapid, can you comment on the feasibility towards the understanding of mole-to-mole reaction between pollutants and the radical generator of phentons?
So, could you repeat the question?
Question is if you can explain how is the reaction mole-to-mole between the pollutants and the radical generate in the Photo-Fenton reaction, and the feasibility towards the understanding of mole-to-mole the relation between both.
Yes, the system, from a chemical point of view, the system is very complicated. We have many reactions, a myriad of reactions. If we want to consider mole-to-mole every reaction, it will be impossible. So the only way to have a kinetic model is to put attention only in the main reactions, discarding the secondary reaction or those that are less important. For example, in a real wastewater, we can have 100 or more micropollutants at concentration of nano or microgram per liter. But in the same medium, we have 10 or 20 milligram per liter of dissolved organic matter. This dissolved organic matter reacts with the hydroxyl radicals too. So we need to pull all this reaction in only one reaction, organic matter with the radicals, and only to pay attention to a few micropollutants, a few key micropollutants to follow the kinetics. It's impossible to follow all the kinetics.
Okay, thank you very much, Jose. We have two questions from Professor Lipuma. That is, the first one is, why can we never reach 100% removal of the contaminants with Photo-Fenton?
It depends of the level of the concentration, of the initial concentration. When we work with very high concentration, tens of hundreds of milligrams per liter, it's much better and cheaper to look for a partial mineralization in order to increase the biodegradability and remove the organic matter with a biotreatment than continuing the Photo-Fenton, the advanced oxygen process up to the complete mineralization. And when we work with macro contaminants, we have to keep in mind that the microcontaminants are 1,000 or 100,000 times lower in concentration than the remaining organic matter in the secondary effluents. So it's almost impossible to reach the mineralization because the treatment times will be very large.
Mm-hmm. And Professor Lipuma has a second question. In the plot used to calculate the treatment capacity as a function of liquid depth, it shows there is the strong lines for different treatment times. Are these lines always straight or not?
In the application of the model, in the region of interest are straight. The lines are straight. Okay, the slope is constant in the region of interest, but we have not extended the model to other regions.
Okay, there is one question more from Paula. She said that she's working in the University of Luxembourg, working on the use of Photo-Fenton with the complex EDDS with a ratio 1:1, but using lamps of UVC of I don't know if mercury lamps or not, but yeah, it's medium pressure lamps of UVC. And she said that she has some problem with the complex because the iron is deposited and attached on the lamp surface.
Yeah.
Do you have any idea why can be having that? Or
increase the turbulence.
Turbulence. This is
yeah.
to increase the agitation. Mm-hmm.
Yeah.
Okay, and there is one more, please. Okay, I would like to know if it is possible to perform the same process in a CPC pilot photoreactor.
Of course, of course. CPC are an alternative to reservoir reactor.
In fact, this is the origin of Photo-Fenton is the CPC, no, the raised weapon reactor. Okay, up to now, we don't have more question in the chat.
Jose Antonio, if we do not have more question, I would like to thank Jose Antonio for the really nice presentation. And before you leave, I would like to inform you, as I wrote in the chat, that the next webinar will be held on May 23 by Professor Cesar Pulgarin. If Cesar is still in the meeting, I would kindly ask him to briefly introduce in 1 minute his webinar. So I think it could be really useful for PhD student and young researcher.
Yes. What is the date? 23. Not that.
I think 23. Yes, we will inform.
I probably did a mistake because it's 21. May 10, 21 is Friday because 23 is Sunday.
Cesar, we will check because in your email you wrote 23,
I did a mistake. It's okay. We will correct that, but I would like next time to discuss with you about some errors I did myself in my careers working with advanced oxidation process. Then I will share with you these errors, and from my experience, I would like to propose not a general rule, because you know nobody has a general rule, to give you some tips that could maybe avoid to you to do the same errors I did at the beginning of my career. Concerning that will be concerning the conceptual limitation, the engineering limitation, the way to sometimes to be too much over enthusiastic regarding the application. You know, sometimes people work in the laboratory level, at the bench, at the laboratory level with the 10 milliliters of water, and from that he will propose a treatment of thousands of cubic meters per day in a Wastewater treatment plant. You know, these kind of things all people we did at the beginning of our career. I would like to stress this point, especially for young PhD students and young researchers.
Okay, thank you, Cesar. I just checked the agenda. Yes, it's the
yes,
23.
I did a
mistake. Is Sunday, so it is 21.
I did a mistake because I did a mistake with April. Yes, I want is 21. Excuse me.
Okay. We will deliver soon the information for registration. Okay.
Yes.
Okay. So, bye. Thank you on myself, Jose Antonio. When you have the link to the video, you can send me for dissemination.
Of course.
The registration of the video is.
Yes, for sure.
Thank you. Bye.
Thank you.
Bye. Thank you.
Bye.
Bye. José Antonio,
Sí.
tú que no te has ido, dime, ¿y cómo haces con el hierro luego? Porque ya pararon. Yo tenía algunas preguntas, pero como yo pregunto tanto, te lo voy a preguntar a ti. Oye, ¿y qué impacto tiene en el proceso la recuperación del hierro? Que a veces la recuperación del tejido es muy costosa, ¿no es cierto? Porque tú necesitas poner a pH neutro, decantar, después necesitas...
No.
Aquí, ¿cómo haces con el hierro?
César, a ver si te puedo...
Yo vi que las concentraciones de hierro eran muy pequeñas, entonces ustedes no recuperan el hierro. Ese hierro se va y lo utilizan en el riego.
No, lo retiramos. A ver si encuentro dónde tengo yo... Oh, Dios. ¿Seré capaz de encontrar la presentación? La diapositiva. Voy hacia atrás. La estoy buscando, César, para mostrártelo.
Bueno, pero si no la encuentras, me la dices, tú la lees y me la dices, la cuentas, que yo te escucho.
La tengo y te voy a compartir la...
Bueno. Qué pena que... Bueno, pero no importa, es así. Sí, no, sigue, no. Qué pena que se acabó como tan rápido. Pero
bueno, nosotros podemos quedar un rato ahora ahí preguntando. No te preocupes.
Dime entonces,
Mira,
yo veo ahí que tú lo recuperas, o sea que tienen que,
mira,
claro, después tienen que
¿este de quién va?
neutralizar de
Este
nuevo.
es un vídeo este es el vídeo de la operación con 15 centímetros de profundidad.
Ya.
Entonces tenemos una columna, en este caso físicamente la estás viendo, de neutralización, porque era un experimento a pH ácido,
Ajá.
en el que en la columna le metemos calcita, ¿no? Carbonato cálcico.
Claro.
Y entonces en la calcita el agua se neutraliza, sale a pH 6 y poco, ¿de
Sí,
acuerdo? Es decir, no está optimizado todavía, pero a pH 6 es prácticamente neutra. Y el hierro se queda retenido en el cuerpo del filtro.
ya.
Y lo mismo queremos hacer para pH neutro, porque el hierro que precipita, conforme se va degradando el complejo,
Sí.
ese hierro lo podemos retener en el filtro.
Bueno, y me imagino que más tarde van a hacer ensayos de capacidad de esos filtros. Porque
Claro,
como,
ahí lo tenemos aquí. A ver si te enseño la planta. Es que de planta tenía pocas fotos. ¿No? Aquí tenemos filtros, ¿los ves?
sí, ya lo veo, sí, el azul.
Sí. Este es el tanque de alimentación del reactor y este es el tanque de salida, del agua de salida.
Ah,
Y este
ya,
es el tanque de filtrado. Es decir, vamos a filtrar siempre el agua. Bien para
ya.
neutralizar o solo para filtrar.
Y después, bueno, y me imagino que luego van a estudiar la posibilidad de recuperar ese hierro, no sé, o no. Ese hierro después
No, porque es muy barato. No
es muy,
merece la pena. Yo creo que es más caro recuperarlo
claro, es muy
que
barato
desecharlo.
y no es problemático ambientalmente.
No es un residuo tóxico.
Oye, y la última preguntita, si me permites, entonces, con relación a los estudios de ciclo de vida y todo esto, tú sabes que hoy en día todos los sistemas tecnológicos en Europa tienen que pasar por eso, es decir,
Sí.
que los ciclos de vida, entonces ahí la integración de la energía grises, las contaminaciones grises en el agua oxigenada, en todo eso, eso también lo están trabajando, lo tendrán que trabajar un día, ¿no? Si
Eso
quieren,
está previsto dentro del proyecto Ulises. Este proyecto europeo,
ya.
uno de los grupos es especialista en análisis del ciclo de vida y lo vamos a hacer.
Bueno, ¿te puedo hacer otra preguntita más?
Las que necesite César.
Mira, tú diste unos valores por metro cuadrado, dijiste que por 25 metros cuadrados más o menos trataban 1 metro cúbico de agua, 4 por 100 y por día. Eso cuando tú lo comparas, si hicieras con la misma superficie en reactores CPC, ¿tendrías diferencias o no tendrías diferencias?
Claro. Es que en ese caso, mira, voy hacia atrás.
A nivel solamente de cantidad de cargas.
Claro, en este caso, estos 4 metros cúbicos por metro cuadrado y por día es con una profundidad de líquido de 20 centímetros.
Son 4 metros cúbicos, así 25 por metro cuadrado y para tratar 25 metros cuadrados para tratar, espera, yo anoto, para tratar 1 metro cúbico por día. ¿Estoy bien?
100 metros cúbicos por día.
Sí, porque son 400. No, repíteme entonces, 25 metros cuadrados para tratar 100 metros, no, para tratar 100 metros cúbicos por día.
Sí,
100.
claro.
Claro, no, por eso era que yo estaba interpelado porque me equivoqué. Yo soy disléxico y me equivoco a menudo en todas estas 100 metros cúbicos por día. Perfecto. Uy, esto es casi 10 veces más. Esto es
Es
casi
mucho más que el CPC.
10 veces. Yo ni siquiera, yo estaba comparando con CPC, pero con TiO2. Es casi 10 veces más rápido que los valores que yo tenía, pues con TiO2 ya no trabajo, pero para tener con qué comparar, es casi 8 a 10 veces más las
César,
cargas más rápido. Qué bien eso. ¿Sí?
César, en el caso de un CPC, el volumen iluminado por metro cuadrado está en torno a los 10-11 litros, 10-11 litros por metro cuadrado, mientras que en un reactor Raceway, solo con 5 centímetros ya está iluminando 50 litros por metro cuadrado. Y si te vas a 20 centímetros de profundidad, estamos hablando de 200 litros por metro cuadrado. Aunque la parte óptica no esté optimizada en un reactor Raceway,
Sí.
que obviamente en un CPC sí que está optimizada la captación de luz, pero realmente como estás iluminando tantísima más agua, pues realmente por eso la capacidad de tratamiento es tan alta.
Bueno, otra pregunta, muchachos. Tú presentaste sistemas donde había continuo estricto, es decir, que tú tenías una alimentación, eso iba y giraba en el reactor y salía por el otro lado el mismo flujo que entraba, ¿no es cierto? Pero el reactor final, el grande, es un batch.
No, el grande se va a operar en continuo también, César.
Pero lo que presentaste es en batch, ¿cierto?
Sí, lo que presenté en batch porque es el primer experimento, el primer test.
Ya, perfecto. Dime una cosa entonces con relación a ese tema ahí. Bueno, eso ya me quedó claro. Permíteme que yo lo anoté por acá. Dime una cosa, ¿cómo anda? Yo creo que el único límite, esto lo veo maravilloso, José Antonio, entusiasmante. El único límite que le veo es la naturaleza de las aguas. Evidentemente no tienen que ser muy ricas en sustancias volátiles tóxicas, en solventes cancerígenos, ni nada,
Claro.
porque con la evaporación y el viento y todo esto puede ser problemático. Es decir, difícilmente lo aceptarían la legislación para cosas así muy tóxicas, ¿no? Volátiles y tóxicas.
Claro. En este caso, como son aguas de secundario de una depuradora,
No hay problema.
Está diseñado para tratamiento terciario de depuradora. Sí. La agua no tienen ese tipo de tóxicos porque vienen de estar expuestas al aire. Los sedimentadores secundarios están abiertos.
No, tiene razón, no, en este caso no hay problema, pero yo estaba imaginando para otros tratamiamientos.
Para otros tratamientos se podría ver la manera de cerrarlo. De todas maneras, lo que tú has comentado de los LED, y nosotros estamos trabajando también. De hecho, ya tenemos datos y queremos mandar una publicación pronto con LED de ultravioleta C.
Pero no te obsesiones con el UVC, porque es que ahí con el Fenton, el Photo-Fenton no necesita UVC, porque cuando miras el espectro de absorción del Photo-Fenton te darás cuenta que su actividad mayor.
También.
¿Ah?
Con ultravioleta A, y lo hemos hecho. Tenemos una publicación también de hace unos años con ultravioleta A.
Y eso sí,
pero es más lento.
Y eso que sí son baratísimos ahora. Sí. Inclusive vi en esta venta china, esta cosa de venta en línea en China, Alibaba, que ya hay VC LEDs también mucho más baratos. También en eso ya han bajado los precios. Bueno, oye, tenía una última preguntita. Tú hablaste cuando presentaste los mecanismos, que la reacción de transferencia de carga entre el hidroxiférrico y con la luz para reformar el hierro 2, que eso era muy lento.
Sí.
Esa reacción. Tú diste un valor en la página, ¿qué página? En la 23, por ahí diste un valor. Sí, en la página siguiente diste el valor, me parece, de la reacción 2. La cinética, sí, la constante.
Bueno, aquí tiene la constante cinética de ser esta.
No, la 6, no, la que tú dices es la 2, ¿no? La 2 es la reacción de regeneración. De regeneración del hierro 2 a partir del hierro 3. Vuélvete para atrás, donde tú presentaste. Ya, empieza de nuevo. Ahí, espera, ahí, sigue.
No, entonces aquí.
Llega ahí, ya ahí. Entonces dice que es muy lenta, pero tú tienes el valor de la de arriba, eso es como 700 y algo, ¿no es cierto?
Este valor es el que te he dicho antes, que es 4,56 milimolar por minuto.
¿La cual? Esta, 4, sí. Y después dijiste que esta era muy lenta. Y esta
es lenta. Esta es lenta en comparación con esta.
Con esa, pero ese valor lo tienes en la 19, me parece. Vea la 19, la de la 2. Porque esta me imagino que es la K2. Ahí está.
No, es que estas constantes no son. Espérate, me voy hacia atrás.
Ya entendí. La 2, no, es que estás con los complejos. Sí, no tienes el valor ahí.
Aquí pero el valor tampoco depende, porque el valor depende de la absorción de fotones. No hay un valor fijo.
Estoy de acuerdo, claro.
La reacción
sí, pero es el orden de magnitud. Yo me la esperaba más rápida esa reacción. Eso tengo.
No, pero no tenemos orden de magnitud de esta reacción en sí directamente. Mira, la reacción 1, en este caso, lo que pasa es que no he querido detallar mucho más, es esta. La del complejo absorbe radiación.
No, ya entendí. No, perdona, ya entendí. No, es que yo estaba hablando de la reacción clásica en el Photo-Fenton ácido con los complejos hidróxidos de hierro 3. Que es mientras que tú estás hablando de la EDDS. Ya entiendo. No, es que esa reacción ácida, Photo-Fenton ácida, pH 3, de los
pero esa reacción la tengo aquí, mira.
hidroxi acuacomplejos.
Eso te lo voy a enseñar, la tenemos aquí, pero no tengo el valor de la. A ver si...
Justamente, sí, porque esa sí, eso no es lento, esa reacción.
Aquí está la reacción. Tú dices esta reacción.
Esa reacción, la reacción 2.
La reacción 2, pero esta reacción realmente depende del VRPA.
Sí.
De hecho, este modelo ya no lo usamos.
Sí.
Este modelo está obsoleto, lo que pasa es que lo tenía en la transparencia y lo he dejado, porque no quería profundizar en los modelos. Nosotros a pH ácido utilizamos un modelo actualizado de esto.
Ya. Oye,
entonces, el hierro 3 absorbe radiación y entonces la constante cinética directamente el VRPA.
Ya entiendo. No, eso yo he trabajado mucho con nuevos sistemas en laboratorio y tal, y por eso me extrañé, porque es una reacción rápida, pero depende del flujo fotónico y tal.
Pero es rápida, pero yo en este caso puse lenta en comparación con esta.
Con la otra que es instantánea.
Porque lo que limita el ciclo de hierro 2 a hierro 3, este ciclo, lo que lo limita no es esta reacción que es muy rápida, sino esta que es lenta.
Ya, eso mira.
¿Sigue?
Sí, ya no, es que uno está acostumbrado a presentar eso más bien el Fenton oscura con relación al Photo-Fenton, y ahí es al contrario. Esa reacción es rapidísima con relación al Fenton oscuro. Perdón,
claro.
la reacción del cuando está oscuro, cuando no hay luz,
claro.
que transforma, que utiliza el agua oxigenada como reductor, no como oxidante.
Es aún más lenta que esta, mucho más lenta, 10 veces más lenta que esta.
De acuerdo, pero cuando lo que comparas con esta, esta es más rápida que esa, ya.
Justo.
Bueno.
Pero en este ciclo, de las dos reacciones, esta es la rápida, la oxidación es la rápida y la fotorreducción es la lenta.
Bueno, oye, muchachos, muchísimas gracias, oye. Yo ahora me voy ya, qué bien, muy interesante, oye, muy chévere, da posibilidades de resolver problemas y todos los felicito.
Gracias.
Un abrazo para ambos.
César, un abrazo muy grande. Tengo pendiente contigo invitarte a que dé una charla.
Con mucho gusto, eso lo veremos luego cuando sea presencial, oye.
Eso es lo que quiero, estoy esperando ya a ver si es presencial, porque sería un gustazo poder que viniera.
Bueno, con mucho gusto, muchachos. Que les vaya muy bien. Un abrazo para ambos.
Un abrazo, César.
Chao, que estén bien. Chao.
Hasta luego.
José Antonio, there is 2 questions more in the chat. I don't know if you can read directly the chat or not.
Tell me.
There is one question from Maria Clara Sterling. Considering.
Where is your question?
No, you got. Okay. She said, considering increased cost associated to the addition of ETDS and other iron complexes, what is your opinion about the intermittent iron addition strategy to enable operation at neutral pH? Is a feasible alternative?
With Maria Clara, nice to meet you electronically, and greetings from Almeria. We worked some years ago with this strategy, with intermittent addition of iron, but finally it precipitates. So you have a lot of iron precipitating in the medium. We have papers with this strategy. I think it's better to use a cheaper complexity agent than adding iron.
There is one question more from Elisangela. Can I make just question? It was used any pretreatment such as microfiltration or sand filtration on the application on the large scale system, or the filtration is just at the end of the process?
There is a sand filtration just at the end of the secondary settlement. In the wastewater treatment plant, the secondary effluent is sand filtrated before sending to the Photo-Fenton reactor.
Mm-hmm. Okay, and also Sandra has Sandra Alzate. Hello, Sandra from Almeria. Ask us about the how will you resolve the acidification or carbonates adjustment when you working in continuous mode operation?
With a acidification chamber.
Mm-hmm.
Now it is installed in the reactor, in the plant.
Okay. I think with this last question, we can conclude with the webinar. Thank you very much for everybody that has been interested in the webinar, and obviously thank you very much to José Antonio Sánchez for this special presentation, a very good, very nice presentation with the last advances in the group.
Okay. So thank you, everybody. Bye-bye.
Bye-bye. Mm-hmm.